Hi, I'm Gaurang and I'm a part of the Application Science team at Elucidata. In this presentation, I'll be walking you through an introduction to disease survival prediction, an active application area for biomedical data and machine learning. We'll begin with a quick introduction to what survival analysis is and why survival prediction is an important biomedical problem to solve. We'll then briefly cover how biomolecular data and ML can be leveraged to address this problem. I will particularly highlight some peculiarities of this problem as regards the data and the modeling itself compared with more conventional ML, which will be notable if you are a data scientist taking up a project in this area. So, what is survival analysis? In a nutshell, it's a set of statistical methods to describe data that's in the form of events of interest, events that occur over a period of time. Let's begin with a simple general example. Let's say we want to know how long did people born in the early 20th century live on average and how uniform the lifespan was across the population. One way to go about answering this would be to gather census records on birth death data, which is of course in terms of calendar dates, align the data for all people by birth date, and then plot how many or what fraction of people survive to different ages. So this is the logic behind survival curves, which are quite ubiquitous in analysis of event data and can reveal interesting statistical trends. The figure on the right compares the survival curves for people that were born in the US in different eras over the 20th century. And in a sense, this comparison reflects the development of medical science itself over the century. It shows, for example, that a lot more people born in the 90s are expected to survive to older ages and past childhood compared to people born in the early part of the century, presumably reflecting advances in medicine and public health, like antibiotics and vaccination. There's also this flattening of the curves with time, meaning that most of the mortality has progressively shifted to later ages, meaning fewer premature deaths and typically longer life expectancies. Here's a more specific application of survival analysis, evaluating response to therapy in clinical trials. In this trial conducted on lung cancer patients, two groups of patients were given different treatments and their relative survival curves were compared. The curves clearly separate out here, not just visually, but also in a statistical sense, suggesting that one treatment might be working better than the other in improving patients' prospects. Another detail to note here is that the events here are not survival per se, but the time to relapse of the disease after initial treatment. So this is another thing about survival analysis. It's not just about survival. The association with the term survival is more of a historic remnant, and it was mostly applied to mortality data for a very long time. But with the past few decades, of course, it has found applications in a diverse range of fields, not just in medicine, but also beyond in economics, manufacturing, and so on. So survival analysis is useful for revealing statistical trends in the event data. But that's not all really. Going a step further, it's also of interest to zoom in on the individual differences in survival outcomes. For example, in a very fatal and aggressive disease, a small group of patients might survive much longer than the rest, even after correcting for obvious differences like age or treatment. So what explains this variability in outcomes? Or why does a bunch of patients show adverse reaction to a new drug, but the majority of patients don't? So these finer differences are interesting, and even more so is whether these differences can be predicted from clinical measurements. So in a sense, this is what survival prediction in the context of disease is about. Having an informed estimate about the likely course of the disease in a given person, and then discovering factors or biomarkers which enable this kind of prediction. Here it goes without saying that the prediction implied here is quite different from, say, predicting the course of Halley's comet in the sky. So in the biological domain, prediction is a relative notion and essentially evaluated by the degree to which it's found clinically useful. And indeed, survival analysis can ideally have translational value for supporting clinical decisions. Outcomes from a survival model can potentially inform the selection of the most effective treatment for a patient, help improve the safety and efficacy of clinical trials, guide the repurposing of existing drugs, and on a more foundational level, even contribute to a better understanding of the disease itself. But how do we find those prognostic biomarkers for a condition? Well, we go and ask the data itself. As we may not yet fully understand the workings of the disease and the complex physiology of the human body, a more data-driven approach could guide us to the relevant predictive indicators. With continuing advances in technology, it's now possible to gather a spectrum of biomedical data about a person's state of health. This ranges from clinical lab reports to physiological readouts, all the way down to final molecular data about the affected tissues, say from a biopsy or a blood sample. But this deluge of data creates the other problem of too much. Which of these many measured variables are relevant to the prediction, and how do we separate out the wheat from the husk, that is the useful signals from the irrelevant information? So this is where machine learning methods can help. The strength of ML lies in its capacity to combine different forms of data, tease out predictive features, and fit models that generalize well, that is, make useful predictions on new patients. So survival data presents a promising opportunity to apply ML to a biomedically impactful problem. So if you are, say, ML practitioner about to embark on survival prediction using ML and biomedical data, especially molecular omics data, what are some of the peculiarities of this problem setting to be kept in mind? For example, how is this problem distinct from, say, the Titanic survival problem that so many of us have seen on Kaggle? To begin with, survival analysis typically relies on mid-sized data sets comprising thousands or often only hundreds of samples. In contrast, each sample is represented by tens of thousands of features or variables. So this is a high dimensional setting where the number of features far exceeds the number of samples, requiring suitable feature reduction or pruning to avoid the usual problems like overfitting. Availability of suitable or usable data is a bottleneck to training ML models here. So this is quite different, quite a different situation compared with traditional ML applications in imaging or language tasks. And in fact, this puts the spotlight on the data itself. Trained ML model is only as good as the data is fed. So careful attention to the data set construction, its suitability for the problem, its quality, these become crucial considerations for getting the best out of the data that's available and improving model performance. So a data-centric perspective, as much or even more than the model or algorithm choice itself, is expected to be a decisive factor in coming up with robust prognostic models. So how do we approach a survival prediction problem in practice? The first step is selecting the right data for the problem, constructing the data set. If public data or data from previous studies is to be used, then it's crucial that the data is properly annotated. So the quality and completeness of the metadata are very important. The omics data itself could be technically sound, but if it's not findable, if it lacks context, then that's going to compromise its usability for a specific problem case. So let's break this down into a few specific aspects of the data to focus on. And let's go over them one by one with some examples. The first step is selection of the patient cohort. For example, if survival is to be predicted for patients with primary cancer diagnosis, then samples from secondary or metastatic disease cases or pre-treated cases should be excluded. The data the model is trained on has to be representative of the population that it's eventually going to be applied. For instance, if the model is trained on a younger patient group, then it may not give meaningful results when tested on older patients due to expected age-related differences in the course of the disease. It's obvious that metadata information here becomes crucial to be aware about the scope and biases in your data set. Another example of cohort selection involves the time of sample procurement, say from surgery. Let's illustrate this with the example of the Cancer Genome Atlas, which is a reference data resource for cancer studies. The sample metadata in TCGA gives the survival time relative to the time of diagnosis. But for survival prediction using omics data, survival has to be ideally measured from the point at which the sample was acquired, say with a biopsy. The sample collection time is not always available, and it can be quite uncorrelated with the time of diagnosis. The figure on the right compares the survival curves using either the time of diagnosis or the time of sample collection or sample procurement as the reference. And it's quite apparent that the survival data looks quite different in the two cases. So details like these about the choice of reference time may seem minor, but they can have a significant impact on the model. The next step involves choosing the outcome to be predicted by the model. This depends on the requirements. In cancer studies, it's routine to use either the time to death, like the overall survival, or a shorter endpoint, like the time it takes for the disease to relapse or progress to an advanced stage following initial treatment. So given a disease context, what's the appropriate endpoint to model? This is decided by how complete the data is. So missing or ambiguous data is an unavoidable feature of real-life survival data, especially when the disease progresses slowly over the course of years. Many patients can be lost to follow-up, or the study period might come to an end before the patients reach the tracked clinical endpoint. So patients with missing data are said to be censored, and even though survival models are designed to handle censored data, the proportion of censoring can impact the performance of your model. So if it's an aggressive disease with a short-term survival, then overall survival might be a reasonable endpoint to predict. But if for diseases that run over a longer course or are more likely to be modulated by interventions like treatment, shorter endpoints like the time to recurrence of the disease might be more appropriate. Again, looping back to our example of TCGA, the figure here compares the proportion of censoring across different cancer types. It shows, for example, that survival data for an aggressive cancer like mesothelioma or GBM, which is glioblastoma, with dismal prognosis is more complete here. There's less censoring than, say, for cancer types which have typically longer survival or are more responsive to treatments. Next, we come to the issue of data quality and what it means for survival data. The notion of data quality lines up along many axes. For molecular omics data, data collection typically proceeds through three broad stages: the sample collection, the clinical annotation, and the measurements, say with deep sequencing technologies. Quality considerations apply to each of these steps. Let's look at them one by one. First, are the samples collected of good quality and representative of the disease? This can be hard to assess in a downstream reanalysis of published data, but sometimes visual inspection of the data with unsupervised methods could help catch suspect outliers. There's this example of a study of glioma, an aggressive form of brain cancer, which used gene expression profiles collected from biopsy tumors. So when they performed initial clustering of the data, it turned out that some tumor samples split away and grouped together with the normal samples present in the data set. So they went back and reanalyzed these suspect tumor samples and found that they contained a lot of non-cancer tissue. So these samples were excluded due to possibly improper sample collection. So this is an example where preliminary data exploration helped identify outliers in the data. Next comes the annotation, of course. As I mentioned before, missing or incorrect metadata can compromise the usability of the data or introduce errors in the downstream analysis, even if the omics data itself is of high quality. So this is where access to complete and curated metadata can add huge value. Our own data platform, Poly, leverages ML-aided curation to improve annotation of public data and fills a crucial gap in data usability. Finally, coming to quality of the measurements, there is possible technical errors to be aware of, which can be detected through initial quality checks. But in addition, other unwanted non-biological sources of variation can also creep in, say due to the experimental design. So these so-called batch effects are known issue in the field, and methods exist to correct them. They can especially arise in the larger data sets where all the samples might have been processed under different conditions or in different labs. or platforms. So again, detection of such batch effects relies on appropriate metadata, like say timestamps or the source laboratory. And this can also be aided by data visualization using PCA or TSNE. After data quality comes the question of the data type that's right for your problem. Say you have a large cohort of a particular type of omics data and you would like to train an ML model to predict survival. But it's a good idea to pause and ask if that data type conveys enough information to train a prognostic model. Different data types might differ in the degree to which they inform survival prediction. So here's an example from an analysis of survival in glioblastoma, a particular form of brain cancer with very poor prognosis. The table on the left compares the survival prediction using different data types that were present in the TCGA cohort. It shows that only genetic markers, certain mutations, do a decent job at prediction, and not the other data types. In the right figure, the prediction performance of a single data type, gene expression profiles, is compared for related diseases. Here, it's different grades of glioma. Again, the differences in predictability are quite apparent. So examples like this one illustrate that there can be differences in the value that a data type brings to a given problem setting, and it's good to be mindful of this possibility. Another complementary question is, how many data types do I need for the problem? As it becomes increasingly common and easy to collect different forms of data, omics data, it's good to ask if more is always better. Measurements, of course, incur costs, and if sample collection is going to be a part of your project, then it is relevant to ask if adding more data types brings significant benefit to your specific problem, as opposed to a judicious choice of a single data type. Finally, when it comes to applying ML to data, it's equally important to ask if the quantity of training data is adequate. Can the model learn predictive features from the data available? For some disease areas, curated large data sets may not be readily available. And even if they are, lack of metadata could limit the availability of usable data. So in such cases, the option of bringing together data from multiple similar studies to scale up the training data set could be considered. This can be loosely viewed as a form of data augmentation. However, this can have pros and cons. When you're pulling data from diverse studies, it's important to address the technical or irrelevant variation across the data sets. The data from different sources, of course, needs to be standardized, made compatible before it's fed to the ML model. On the positive side, the pooling of data sets can help build a more diverse training set that better emulates the real-world distribution of the data, especially when it comes to validating the model. Use of external data sets, that is, the data that was not used for the training, is a generally recommended practice to ensure that the model generalizes reliably to novel test cases. So once we have constructed a data set for ML, how do we model it? Survival in general can be framed as either a classification or a regression problem. If the goal is to predict a clinical endpoint related to a fixed reference time, then standard techniques like logistic regression or decision tree classifiers can be used to fit the data. An example in practice is the FDA-approved MammaPrint assay for breast cancer diagnosis, which predicts cancer progression within a 5-year window. A drawback of this approach classification is that the accuracy of the model may depend on the choice of the cutoff used. On the other hand, if a more granular prediction is needed, then continuous time survival models are preferred. There are advantages that they can handle censoring or ambiguous labels well, which, as we have seen, is quite common in the context of real-life survival data. One popular choice is the Cox proportional hazard model, which essentially predicts the probability of survival to time t given a bunch of input variables, covariates about the patient. So this model makes some assumptions about the distribution of the data, so it needs to be checked if it applies to your data set. But in general, it enables better utilization of the event data at hand compared with more conventional regression or classifying methods. Finally, we come to the last part, evaluating a trained model. What are the right metrics to assess the performance of the survival prediction model? In ML, metrics like accuracy, FN scores, mean squared error are conventionally used. These are not so routine in survival prediction, where it's more common to use other metrics. To get a sense, let's say we have predicted a risk score, which is equivalent to the expected time to event survival time for every test case. And these are the cases are ordered or ranked as per their risk scores. From these sorted predictions, two metrics are often computed. One is called the Concordance Index. The C index is a number between 0 and 1, and it reflects the general level of agreement or consistency between the predictions and the ground truth event times for every pair of test cases. The better the agreement between predictions and ground truth, the closer the C index is to 1, and a C index of 0.5 corresponds to a null baseline. Another related metric is based on dividing this ranked list into two predicted groups, a high-risk group and a low-risk group, and comparing their true ground truth survival profiles. If the model makes sensible predictions, then these stratified groups, as they're called, should separate out clearly, that is, show distinct survival courses. So there are measures like hazard ratio and log rank test statistic to quantify these differences, and better models are associated with wider statistically significant differences in survival. In addition to metrics of performance, it's also of interest to view a survival model through the lens of practical utility. After all, survival prediction is not just a theoretical exercise. It's intended to provide actionable outcomes which could inform clinical decisions. So a proxy measure of clinical utility is provided by the number of features in the trained model, how many measurements are needed at the very least to make reliable predictions. So there's this implicit practical trade-off between performance and model size. And simpler models are more likely to provide scalable, cost-effective solutions. This notion of model selection or feature selection is somewhat implicit in the training methods. For example, regularization of ML models reduces the number of features in the model. However, this can also be introduced more formally into the model fitting process, like by using optimization methods that more directly try to find models which are sparser and involve fewer measurements. So in a nutshell, prognostic models need to be not just accurate enough, but also usable. So this brings me to the end of this overview on survival prediction. To recap very briefly, ML, together with traditional survival analysis, can help extract prognostic information from biomolecular data. These biomarkers can have translational impact potentially and support decisions around disease treatment and drug discovery. And there are FDA-approved biomarkers as well now, reflecting their perceived clinical utility. But it has to be remembered that molecular omics data has its quirks, and fully realizing its potential for practically useful survival prediction will require a domain-aware understanding of the data journey from sampling connection to its eventually use in tabular form in the downstream modeling process. Thank you for your time.